At a top-tier Indian engineering college, Naksh felt like a lucky guesser. Surrounded by brilliant peers, he sat convinced his admission was a clerical error. Then there was Lal, a teaching assistant who spent his time sliding complex entrance exam questions across cafeteria tables, constantly pestering students while they tried to eat. Lal was operating under a hidden mandate. He was an undercover auditor for the Board of Credibility, tasked with weeding out students who had merely memorized their way into the college. Lal targeted Naksh with a highly complex fluid dynamics problem, sliding the test across the table to see how he would react. Naksh solved it without reciting a textbook formula. He visibly wrestled with the underlying logic step by step to arrive at the correct answer. Naksh finally proved he had true academic grit. Still, Lal checked a box categorizing him merely as a reciter, knowing the math is only the first, incomplete step of true engineering. In the hardware lab, Lal presented a new puzzle, a printed circuit board featuring a 0-ohm resistor. That is, a resistor specifically manufactured to provide zero electrical resistance. Naksh took the literal textbook interpretation. A resistor with no resistance is a waste of money, and a basic piece of copper wire is cheaper and electrically identical. The manufacturing reality dictates otherwise. Automated pick-and-place assembly machines grip standard, rigid, rectangular blocks. They fail when trying to pinch raw, flexible wire. This descending cost curve chart shows assembly unit prices dropping dramatically with standard parts. The 0-ohm resistor relies on automated assembly economics, not electrical engineering. A successful engineer cannot design in a vacuum. They must build for the physical realities of the factory floor. We see the same constraints in software. Take Quicksort, an algorithm that sorts data by continually dividing lists into smaller halves. On paper, it is incredibly fast and theoretically clean. But when you run Quicksort on a massive real-world database, it stalls. It forces the mechanical read head of a hard drive to physically jump and scatter its movements across the disk to retrieve data points. Now consider the bulky B-tree algorithm, which groups data into large, continuous blocks. It succeeds specifically because it minimizes the physical, darting movement required by the mechanical hardware. These hidden rules also apply to human behavior. Take the case of a manager who eliminated employee tea breaks to squeeze out more raw working hours. Cutting those breaks destroyed team productivity. The manager inadvertently wiped out the primary informal hub where the team exchanged crucial information. Invisible constraints, whether the physical limitations of a machine or the social behavior of humans, will always break perfect theoretical systems. Building tension. Lal eventually presented his ultimate engineering achievement, a high-tech solar power controller designed specifically for deployment in rural Jharkhand. The specifications were impressive. It used highly advanced gallium nitride, or GaN, transistors. GaN is a specialized semiconductor material that handles high voltage with minimal heat loss, allowing this controller to hit a flawless 99% energy efficiency. Yet, shortly after deployment, the local farmers completely abandoned the devices, leaving Lal baffled. Here, the power dynamic flipped. Naksh stepped into the role of evaluator, looking past the mathematical perfection to assess the reality of the rural environment. Naksh discovered a fatal environmental flaw. When one of those fragile, microscopic GaN transistors fails, in a remote village, the farmers have absolutely no way to repair or replace it. Naksh proposed a counterintuitive solution, replacing the advanced technology with a clunkier, less efficient, older-style circuit system. This timeline graph shows exactly why the clunky system is superior, mapping operational lifespan over time. The highly efficient board has a short lifespan that drops off suddenly when it breaks. By sacrificing peak efficiency, the simpler board allows a local farmer to maintain and fix the device themselves, extending its long-term usability. Extreme optimization is useless without maintainability. Naksh's self-doubt was actually the birth of a critical mind. True engineering mastery requires designing for the messy, imperfect reality of the humans who use the technology.